Hello and welcome to our demonstration for NOMS 2020, OvS-DPDK port mirroring via NIC offloading. As SDN-based networking infrastructure continues to evolve, an increasing number of traditional network functions are deployed over virtualized networks. Like traditional networks, traffic monitoring in a software-defined network is critical in order to ensure security and performance of the underlying infrastructure. In the context of virtualized networks, deployment of a virtualized TAP service has been reported as an effective VNF that can provide the same monitoring capabilities as a physical TAP. Unfortunately, over a pair virtualization environment, for example OVS, where inter-VM communication is expensive, it has been observed that virtual TAPs can contribute to up to 70% performance degradation. In this paper, we present a hybrid approach that allows network administrators to mirror vertical port traffic to another VNF, SR-IOV, via NIC hardware offloading. As a result, the mirrored traffic can be viewed through a monitoring VNF and a separate VM. Through this approach, the throughput overhead can be reduced as much as 50%. For our demonstration, we explored three different scenarios. In the first case, we explored a baseline case with mirroring disabled. In the second case, VTAP mirroring via traditional built-in OVS mirroring mechanisms. And a third case, VTAP mirroring via NIC offloading, our unique contribution in this demonstration. The first case we explore is the baseline case with mirroring disabled. The following part of the demonstration shows our VNF performance in terms of throughput for the baseline case, that is, mirroring disabled. Our VNF in this case is timothy.d running inside of a VM. We go ahead and start traffic from our traffic generator, in this case package.n. With traffic now flowing, we go ahead and show the amount of throughput that is available on the VM. In this case, we observe approximately 12.6 million packets per second for throughput. The second case we explore is VTAP mirroring via traditional built-in OVS mirroring mechanisms. For the next test case, we show the throughput on our VNF as before, timothy.d, in the case where mirroring is enabled using the traditional OVS mechanisms. As before, we start traffic using our traffic generator, in this case package.n. With traffic now started, we go ahead and measure the amount of throughput on our VNF. In this case, we observe about 3.8 million packets per second. That is approximately 70% below 12.6 million packets per second. The third case we explore is VTAP mirroring via NIC offloading, our unique contribution in this demonstration. For the last part of our demonstration, we'll be showing the throughput of our VNF, as before, timothy.d, with mirroring enabled with mitigation, that is, via NIC hardware offloading. As before, we start traffic using our traffic generator, package.n. With traffic now started, we go ahead and start measuring our throughput on our DUT. In this case, we measure about 8.8 million packets per second, which in this case is a 30% performance reduction as opposed to a 70% performance reduction with the traditional mechanism of using OVS's built-in mechanism for mirroring. In this case, we note that this is the maximum receiver rate test case. That is, this is not the 0.001% packet loss test case. Thus, our throughput numbers are higher. In this section, we present performance data collected when enabling port mirroring for an OvS-DPDK environment. We compared the performance, as before, of VM network throughput for three setups: mirroring disabled, mirroring enabled, the default case, and mirroring based upon our design. The top right figure shows that although throughput significantly degrades for the default OVS implementation, performance markedly improves and is ostensibly restored by means of our design. Based upon the bottom right plot, we observe that in the default case, there is a 70% performance drop for most packet sizes. For the case where we introduce our design, we observe only about a 30% performance drop when mirroring is enabled. Whereas the previous figures show the maximum receiver test case on XXV710-DI2 NICs, the following figures present the 0.001% packet loss case on XL710-DI2 NICs. As before, with the upper right figure, we observe that there is a significant performance degradation with mirroring enabled in the default case, and throughput is ostensibly restored with mirroring enabled with mitigation. For the bottom right figure, as before, we observe a 70% performance reduction with mirroring enabled in the default case, and only about a 30% performance reduction with mirroring enabled with mitigation. In this demonstration, we have shown a hybrid design to capture and transport VertIO port traffic to an SR-IOV based VNF. The benchmarks related to our design demonstrate a 50% reduction of port mirroring overhead compared to the native OVS port mirroring implementation. For next steps, we plan to formalize this design and work on upstreaming our contributions into the DPDK community.